Leeds International School, Form 4, Second Term, Unit 2, Inorganic Chemistry, the Alkali Metals. Learning objectives are: understand how the similarities in the reaction of these elements with water provide evidence for their recognition as a family element. Understand how the differences between the reaction of these elements with air and water provide evidence for the trends in reactivity in Group 1. Use knowledge of trends in Group 1 to predict the properties of other alkali metals. Let's move on to the lesson. The first thing that we are going to see is what is known as alkali metals. The elements in the Group 1 of the periodic table are known as alkali metals. Those are lithium, sodium, potassium, rubidium, cesium and francium. The one is the bottom, which is francium, is a radioactive metal. One of its isotopes is going to be produced during the radioactive decay of uranium-235, but this is extremely short-lived one. So therefore still scientists believe they may have very small amount of francium on the earth crust, but still no one has seen. But anyhow, when you know about the rest of the Group 1, you can predict what francium would be like. So we will make those predictions later. Let's see what are the physical properties of these metals. These metals are very soft, therefore we can cut easily with a knife, and they are very shiny and silvery when freshly cut, but tarnish very quickly with the exposure to the air. When we talk about the melting point and boiling point of these metals, those are very low and getting lower as you move down to the groups. If we talk about the density of this group, the densities of these metals kind of increases when we go down to the group, and that increasement is not regular increasement. As you can see in this graph also, you can see the increasement of these metals, but those are not regular increasement. And also you can see the density of lithium, sodium, potassium is lower than the water density. All these metals react quickly with water and oxygen in the air, making oxide and metal hydroxide, which is strong alkali. So that is the main reason Group 1 metals are known as the alkali metals. So if you touch these metals with your bare hand, it will produce lots of heat and very corrosive metal hydroxide. Since all these metals are extremely reactive, we should have a great care when it's come to storage and handling of these metals. That is why we keep lithium, sodium and potassium under the oil, and we keep rubidium and cesium inside of this kind of glass tube. Therefore, they cannot contact with water or the oxygen in the air. There are two reasons that we put this element in this Group 1. The first one is they will have only one electron there, outer shell. So if you take a look at these electronic configurations of these metals, you can realize that easily. So you can see even in the lithium, sodium, potassium, outermost shell contain only one electron. So this characteristic feature we can see each and every element of this group. So that is one common thing that we can see of these elements. The second one is they all have similar chemical properties. For example, when they will react with water, they will make hydroxide of that metal and hydrogen gas. When they react with oxygen, they all make oxide of that particular metal. So when they are going to react with halogen also, they are going to be reacting in the same manner. And also they are making ionic compound which contain this kind of M plus ion. For example, they are making sodium plus, potassium plus kind of ions when they make ionic compounds. So the chemical properties basically depends on the number of electrons in their outer shell. You saw at the beginning they have same number of electrons at their outer shell. So that is the reason for they are having this kind of same chemical properties for them. And the second reason is kind of highly depend on the first reason. When we talk about the reaction of these metals with water, all the metal react in the same manner, giving hydroxide and hydrogen. If you take a look at these equations, you can easily identify and understand how this alkali metal is going to be made alkali metal hydroxide with the water. The only difference between the reaction is going to be the speed of that reactions. As we know, when we go down the groups, the metal become more reactive. Therefore, reactions also occur more rapidly. For example, if we talk about the reaction of sodium with water, you can see as in this equation, sodium is going to be reacted with water and it gives sodium hydroxide and hydrogen gas. So during that reaction, we can see some observation. The one thing that you can see is this sodium kind of floats because the sodium density is lower than the water density. Therefore, it is always floats on the water. And the other thing is, this piece of sodium melts into a ball during the reactions. Because its melting point is very low and a lot of heat is going to be produced during that reaction. That is why it is melting. The other thing that you can see is evolving of hydrogen gas. Therefore, you can see some fizzing. And the other thing you can see is sodium moves around the surface of the water. Because hydrogen gas is not going to be released symmetrically around that sodium ball. Therefore, this sodium is kind of pushed around the surface of the water like a hovercraft. At the end, if you check, you can see this alkaline solution has been formed. If you use some indicator, it will show that this solution which is made at the end of the reaction is highly alkaline. And also you can see the piece of the sodium getting smaller and smaller and eventually it will disappear. That means sodium is consumed during the reaction. Likewise, if we take a look at the reaction of lithium with water, it is always similar to the sodium reaction, except the rate of the reaction is kind of slower rather than the sodium, and the lithium's melting point also higher, so therefore heat is not going to be produced so quickly as the sodium. So therefore lithium is not going to be melt during this reaction. And if we take a look at the potassium, that is kind of faster reaction than the sodium, and some amount of heat also is going to be produced because of the ignite the hydrogen, and therefore it's kind of ending up with spitting around and exploding. And the rubidium and the cesium also react more violently, and the reactions can be explosive, because as we know, we go down to the groups, the reactivity always increases. Let's see the reason for this increasement of reactivity when it's go down to the group. In all these reactions, the metal ions are losing its electron and form metallic ions in that solution. So the difference between those reactions depend on how easily that outer electron of the metal is lost during the reaction, and that is going to be depends on how strongly that electron is attracted to the nucleus in the original atom. As we know, if we take an atom has this nucleus and it contains protons. Not only protons. For this lesson, we just consider about the protons. Protons are positively charged. Therefore, normally our nucleus also positively charged. So this positively charged nucleus always attract negatively charged ions, negatively charged things. So the electrons are negatively charged. Therefore, this electron is going to be having some interactions with nucleus. So, as we move down the groups, you can see in this figure as well what happened to this atom is these atoms become big. They are bigger and bigger when it's go to the down. The reason is when these atoms goes to the down, they have more shells of electrons. They are not having only this shell now. So each of these atoms have different number of shells of electrons, and the number of that shells of electron is going to be increases when it's go down. So then what happened? Because of that, these atoms become big. So then what happened? When the atoms get bigger, the outer electrons, which is the one that is going to be lost during the reaction, is further from the nucleus. Then what happened? Because it is further from the nucleus, it is less strongly attracted by the nucleus. Because if you take a look at this figure, you can see this red color one is the last shell electron. And you can see when we go from lithium to sodium, the metallic radius increases. That means the distance in between this last shell electron and the nucleus increases. Therefore, what happened? The attractions between nucleus and last shell electron decreases. When we are further from the nucleus, the attraction force also is kind of losing or decreasing. So therefore what happened? The removing last shell electron getting easier. So that is why when it goes down, it is really easy to remove this electron from the shell. So that is the reason these atoms or these metals are having this much of reactivity. That is why they are increasing its reactivity when it's go down. Let's move on to the reaction of alkali metals with air. Normally, when the alkali metals are cut, they initially appear shiny, but quickly what happens is they become dull and white because they react with oxygen in the air. So this is known as tarnishing. When we talk about the reaction of lithium with air, it is kind of very slow reaction when we compare with the sodium one, because lithium is going to be at the top when we compare with the sodium in the periodic table. So therefore lithium tarnishes slowly because it's relatively slow reaction happening with the air. If we talk about the sodium reacts with air rapidly rather than the lithium, because sodium tarnishes more quickly rather than the lithiums, which gives the evidence for that greater reactivity of the sodium when compared with the lithium. Because let's say if we look at the piece of sodium which has been taken out of the oil, it is usually has a crust on the outside. It is not shiny. But what happens if we cut that piece of sodium? The fresh surface is shiny, but it tarnishes rapidly as a freshly expose that sodium to the oxygen. So think about the reactivity of this sodium. But if we take a look at the potassium reaction, with the air, it is going to be more rapid reaction rather than the sodium even. Because this potassium tarnishes so quickly, therefore it is very difficult to see that potassium as a shiny metal even. So it is again gives the evidence that potassium is more reactive metal than sodium and the lithium. If we burn these metals, we get more vigorous reactions, and it is more difficult to see which metal is most reactive because all the reactions are so rapid. But they are going to produce different colored flame. If we take lithium, it burns with a red flame. If we take sodium, it burns giving orange flame. And if we take potassium, it burns giving lilac flame. But at the end of each of these cases, it produces white color powder. That is alkali metal oxide of that particular metal. If we talk about the compounds of these alkali metals, all the compounds are ionic solids, and most of them are really soluble in water, and they are colorless. But if they combine with colored negative ion, they are going to get the color of that negative ion at the end. Now we know basic things about these alkali metals, and when we move down to the groups in the periodic table, we know the properties of the elements change gradually. So if we know the properties of almost all the elements in that group, we should be able to predict the properties of the elements we don't know in that group as well. So as I told you at the beginning, this francium is kind of very and extremely radioactive, and at any time, anywhere in the world, there is only a tiny amount present, and nobody has seen a piece of francium as well. But anyhow, based on the things that we already know about this group, we can predict the properties of francium. So if we move on to the prediction of this francium is, we can predict that this is very soft metal, and the metal melting point should be around room temperature, because as you know, the melting point and the boiling point is kind of decreases when we go down to the group. And the density should be around over 2 gram per cubic centimeter, as when we compare with the density values of the other metals. And this should be more reactive rather than the cesium, and its hydroxide should be soluble in water and give strong alkali solution. So if we carry on the basic concept of this particular group, we can do this kind of prediction as well for any atom that has in that group. I believe you got the knowledge about the alkali metals. So hope you will enjoy the video. Thank you very much.